Very excited. Go ahead.
Hey, hi everyone. My name is John Yoon. I am in the School of Liberal Art, more specifically cybersecurity. I've been here with Mercy, I think this is my 17th year. Prior to Mercy, I have been in a couple of other major universities in another states. Before joining here, and also I was working in some industries as well. So today, the topic that I chose here, myself and I delivered these concepts to the classrooms a couple of times, but the concept-wise, this is very interesting, and then this is yet another the direction. As we know, there's lots of encryptions and cryptographies, and cryptocurrencies. That those things is not really completely hiding, but it is something we scrambled the information. But another way that we do here, steganography is similar to that, but in a little different angles that I want to share with you. So, start with a taxonomy. I'm going to give you some concept, and then I developed some of the codings, and then I'm going to end with extended works. So starting with the cybersecurity, some of the major topics listed on this slide, but it's almost unlimited. But I'm going to point out something, some area where the terminology steganography can falls in. That is in this information detection, and where there is a counter steganographies and information hidings, mainly in these areas. But the major concepts of steganographies be applied to everywhere here. That I can share with you the last slide of my talk today. Okay, so why steganographies? Actually, it's a hiding information hiding, right? Then encryption is a well known and widely used the concept. But with this steganography, if we compare with the encryption, then encryption is try to shout out, "Hey, I'm scrambled. You cannot read me." That's what encryption does, right? For example, this is plain text. Mercy was built for the first timers and the second chancers. This is some of the catches that I got from Mercy University website. That can be encrypted like this. So we know there's something. This guy says, "Hey, you know what I mean? I'm hiding. I have something, but you cannot see me." That's what encryptions. It's a part of information hidings. But on the other hand, in the same for the same achievement, that is this. Steganography is whispering. So we have something here. I'm not going to tell you, but there is something. Here is a image, photo. So I'm going to hide something here. I can send this to Samuel because we are in the same comrade. We need to share. Hey, here is a time. You need to push the button on this particular time. So I'm waiting for that. That is secret messages. We have to keep it, right? No one can see it. If we say here, then somebody try to break it. See what the message is in this encrypted text. But here in this case, no one knows. I want to hide something here. No one knows where it is, right? So I'm going to give you some concepts, how it is possible. If we want to hide, then we have to first understand the images. So I'm going to tell you how image is not completely well. Image, many of you already understand. There's a JPEG format, there's a PNG, so there are so many others, GIF. Each one has different formats, different compression mechanisms. Some of them do not carry all the bits and bytes without losing it. Some other formats, we don't really care. Some of the bytes, if it is not really important, we need to keep only some important portion of your images. That's possible, right? Then it's more efficient to deliver the image itself. Why don't we have to preserve all the spaces of that images, right? Here in this case, what is more important? I think, to me, maybe this monitor, right? Some other guy may say, hey, there's something behind some of the books. Someone may say something else. But anyway, each spots on the image are not equally important, right? So I wanted to keep that in mind. But the messages that I want to send, we should not lose any, right? We should keep all the messages accurately without losing. So images, some image compression techniques are lossy. Lossy means lossy is allowed. Lossy compression or lossless compression. There are so many different techniques available. For example, JPEG, JPG images, there's a lossy compression. If you take a photo, if it's a JPG formats, if you want to send it a smaller size, then some portion lose. Automatically, you don't really choose which one. But PNG, try to keep almost. And then there is also some other image formats depending upon the manufacturers. For example, iPhone images. None of those. iPhone image is not JPEG, it's not PNG. What is the iPhone images? iPhone images, if we see, it is called JPG, but real image itself, is this shown here? It says a JPEG, but if we read it, it's not. Oh, this is JPEG. But some other images is this, HEIC. This is HEIC formats. Let's see what it is. Yeah, this is a HEIF formats. So each image has different the formats available, right? So, okay. Images, internally it is, even if for that is images, text, the primitive data formats is binary, right? It's a 0 and 1s. This is also 0 and 1s. Text character also 0 and 1s. If we want to, the computer understand the Mercy University, capital M, we see capital M, this is a human readable, but the computer keep this code 01001101. This is for M. E will become different binary code. So all the uppercases, lowercase of the characters and the numbers, some special characters, all of such characters all together, it is not more than 128. 1 byte, which is 8 bits. Each bit can be set or unset. Therefore, 2 codes can be represented by 1 bit. If we have 8 bits, then total 256 combinations possible. So 1 byte long memory space can represent 128, including all. So English alphabets, numbers, special characters, all can be represented in half of the 1 bytes. So we call that lower ASCII code, and high ASCII code can be used for some other languages need more. But anyway, so what we looked at so far, text can be written in binary code, image also written in binary code on computer. So if we hide the text within an images, this we know what it is, right? But if this M is hidden here in this image, it's very hard to see, right? And also if it is spread over this image, it's even harder. So brain cannot detect small pixel changes. What is this, how many pixels in an image usually? More than 1 million, right? Million pixels. 1 pixel, 1 small dot, I would say that is a pixel, okay? If it is a color-coded pixel, then it requires a 3 bytes code, okay? 3 lights can be combined together to construct 1 color, 1 light color, not the paint color, right? So we call that RGB code, red, green, and blue. Red, green, and blue lights can, if we turn on all red, green, and blue, all the lights on, then we call that white. If we turn off all the lights, 3 of those primitive lights, then we call that black, right? In between, little bit of red, a little bit of green, a little bit of blue, because red, green, and blue each, there are how many gray levels? 254, 5, 6, yeah. That many red color, that many green color, that many blue colors. So pure, true red, then maybe we can say 255 coded red. Light red, then maybe 1. Something like that. So how many pixels? If we have 1 million pixels, then actually it requires 3 million bytes. 3 million bytes, then that is, I think, 300 kilo, right? 300 kilobytes images. Usually, if we see here, what is the size of this image? This is almost 300 kilobytes, right? But this is 238 kilobytes images. This is a compressed images. So real images, I think maybe 300 gigabytes images. That many pixels originally created. But when I send this from my cell phones to my computer, it's reduced, okay? Compressed. By compressing, we lose lots of pixels. Okay, so even if this M itself appears here, it's very hard to see. But we do not hide the M itself, we hide 0 and 1s. Also, 0 and 1s are not all together in conjacent positions, but we spread that out. Almost impossible, right? So this is images, but computer shows this, but human cannot recognize it, right? So by knowing this, hey, now we have to develop something, some technologies, steganographies. And human eyes can see only 3 to 5% of data in a picture, right? If we see some of the pictures that I showed here, right? We don't really see much, a little bit of those. And also, depending upon JPEG or PNG, we preserve all the dots. Try to make it lossless. But JPEG, usually that is a lossy. But this has nothing to do with it, not directly related to today's lecture. Not really lecture, presentation. Okay, RGB code. Each can be represented in 1 byte. So in order to represent one color pixel, then it requires 3 bytes long. So if we draw green lights, then we have to turn off all the red, turn off all the blue, we turn on all green, then it'll be true green light color. Idea here, what if we turn this 0 to 1? Is it still green? Yes, it is still green. Only 1 bit difference. Is it 1 bit difference here, the upper bit, or 1 bit at the lowest bit? If it is the lowest bit, then that is the least significant bit. Almost impossible to recognize that bits. If we change this first bit, then maybe a little bit. Let me show you one examples of the code that I made for you to understand. This is written in Python, so I want to run for this color to be, and asking me to enter RGB code. As I said, each light color has 256 grades. So I can choose one of those. So I would say that 100 out of 255 red, and 150 out of 255 green, and 200, we can say percent, it's not percentile. let's say if it's 255, that is 1%, 100%. Then 200 out of 255, maybe 75%. So I can set this 100 degree red, 150 degree green, 200 degree blue. What color do you think it is? So mixed a little bit of everything, right? So I showed to you, originally, this is 100, 150, and 200, right? So all, if it is 100, in binary code, 011001000. Green 150 means 100101110. And the other also. If we see here, I changed it from this RGB. This is given. I said 100, 150, and 200. I changed only one bit. Only this. Blue. I said here blue. Blue least significant bit, I change it from 0 to 1. Then if you compare these two, very similar. Somebody said, to me it's not really similar. I can tell a little bit difference. That's okay. This is one bit. How many bits in one picture? At least 1 million. Sometimes 200 billion pixels, one picture. Out of 1 billion, 1 out of 1 billion. And then that one bit is different. Can you tell it? Almost impossible, right? So we want to change this least significant bit. We want to change only one bit from one pixel. If we change, if we want to hide M from mercy, then M, how many bits? 8 bits. So we want to take one bit from there and hide it 1 pixel. Second bit, hide it in another pixel. Third one in another pixel, and another. All dispersed. Almost impossible, right? However, if we change the first bit, this much difference. So we do not change the first bit. We want to change the last bits. Almost impossible. Last bits, which is 1 over 1 million or 2 million. That's what we want to do. That is the concept behind this steganography technology developed. So it's like this. I want to put these zeros here. This is 1 pixel, RGB, each represented by the 8 bits, which is 1 bytes. So that will be somewhere here. We want to change this. For this second one, we'll go another pixel. And the third one, go for another pixel. Something like this. So dispersed. So I think, so hiding, now we know, right? Extraction, reconstruction. That is the state of the art. But between you and me, Samuel and I, we agreed, I want to hide this here. I want to hide this under the tree here. I want to hide this somewhere there. If we know that, then I can pass my message that is unable to be detected by anyone else but my friend, right? So the simple idea here is this. Anyway, because I want to change the least significant bits. So I want to focus only on least significant bits. But I do not know where it is touched blue code or red or green, because it is RGB. I do not know whether it hide the bits, every pixel consecutively, or I want to change the pixel one after another, or one of every 10 pixels, or randomly, right? So reconstruction is almost, that is, even AI cannot, right? So I'm going to give you a demo. Let's say, this is originally from HEIC, from my iPhone. So I changed it to, because my code itself, I'm going to show to you my code. Yes, although you may not know, right? But this is a hiding code. So some of the x coordinate, y coordinates. This is a two-dimensional images. So I'm reading these images by a bit, and I hide something in some location. The way that I can use, this is the command that I can use, because I made some of the commands on this program. Where is it? So when I see here, Python, I want to see the help, Python help, steganography as hiding. Let me see if I made that. What is my, oh, I didn't make a hide, the help. But anyway, let's see if it does give me any help. Yeah, it has a little bit of help, but not completely well. Well, this is a help, right? X, those. But anyway, so the way that I can do here, I can do Python steganographies, right? And then I wanted to change the directory where that target, this is a JPEG file. I'm going to show this to here, right? This is JPEG file. And I'm going to remove this once, so that is deleted. So where that JPEG file is stored, I want to get that from here, the location. So I want to change this. I want to get the copy of that path expression, and coming back here, and I can do that. So that is path expression. And then XY coordinates, and then I can say, what is the input image? Input image is this, test.jpg. So I can say test.jpg, and where you want to start from the hiding. I said the XY coordinate from the first positions. So I can say X. So my program make it more general, so that I can hide it anywhere in the middle of the images. But and then text, what do we want to hide? So we can say, for example, mercy, cyber security program is, what do you want to say? Huh?
Amazing.
amazing. Amazing. That is a text I want to hide. And then the last one is output. So I want to say it output. So minus O is, I said here test JPG, so that I said test hide dot PNG. Why I'm doing PNG? Because if I convert it JPG, then JPG itself will compress it. So lose some. I want to carry all the bits to my output images. That's what I explained, right? So PNG, and hit enter, then it creates the files. Let's see if there is a, let's see here, there is a test h.png, right? So if we see here, these two images, can anyone see there is a Mercy cybersecurity program is amazing? Almost impossible, right? Our brain cannot read it. Then can we extract it? So there is a, push this aside, and another program called steganography extracting program. So I'm going to show this to you. So this is another program, but we want to extract and reconstruct the original text that we hide. So this is the command that I need to do. So I can do here Python, and then steganography extracting, and then again I need to change the directories. I think I saved the path expression previously. Yeah, that one. And then there's an input. Input is PNG, right? So input test h.png. That images holds the text, the message that I hide, right? And then the other, the parameter that I created, this is only demonstration purpose. I want to extract 2 letters at a time. So gradually we can see, not all at a time, right? 2 letters at a time, 2 letters at a time. So I can say 2. Because my laptop is fading out. By the way, I will have new ones sooner. It'll come out. Yeah. Okay, so these are the hidden ones that extracted and convert it back to letter. So that is ME. 2 letters came up. To continue any key, I can hit any key, but 0 then it stops, right? So I can do any key. And the next one is RC. So first somewhere here that is for ME, and then the next one is RC. And I can keep doing this. So Mercy cybersecurity program is amazing. This is because of the last ones. Last one is a little bit of a mixed, right? If we do a little more, then it is all. I'll show it to you another. For example, if I do amazing and if I do this, then amazing will find the quick. Okay. Remember that amazing, instead of G, it gives the F. That is because of not only that, but it goes all the way, but the last characters is mixed with the original images. That is, I know that because the developer knows it, right? So if we extend that to Mercy cyber security program is amazing and excellent, then that portion amazing is okay. Previously, amazing says amazing, but now amazing, right? And it goes excellent. This is okay, right? Because of this a little bit of that ones. Because I'm choosing two at a time. So unnecessary bits comes in together, so it changes a little. So this is the way that you can see, say, this is original test JPEG, this is the ones, this is not, I converted again, right? This is 239, previously to something else, right? Earlier version. This is overwritten. Okay, so go back to my presentation. Where is my presentation? So I'm going to close. Okay, here. Any questions so far?
We'll probably wait till the end.
Okay. So issue, we know the issues, right? Steganographics variations, lots of variations. Yeah. Where we want to hide it. So which points that we start hiding? How often are we going to hide every other bytes, every other bits, every 10 bytes or whatever? Are we going to hide it in forward direction, or first position that we hide the last position of the images and the reverse way? Many things, right? Therefore, detection must consider all possible combinations of these. So almost impossible, right? For the purpose of hidings, information hidings, if it is hard to detect, then that is a higher success rate, right? Because we want to hide it really completely. This is, yeah. So extended research. You may think this in current popular terminologies, AI or OpenAI, and also we know OpenAI can draw images. What if OpenAI, because OpenAI freely draw, right? The way that I did here, I'm using the images, I open it and hide somewhere. But inventor can hide from the beginning. So this image is actually generated from OpenAI. As it originally generates, it can hide something somewhere. Only OpenAI knows, right? No one else knows. Would it be some cyber threats? Possible, right?
Oh.
I'm not saying OpenAI is a spy, but technically possible. No one knows. There are lots of applications available. One of the things that you all know is stealthy intrusions over your infrastructure, network infrastructures. See, network, there are your computer, if you see in your computer, how many ports are already designed? Or every the laptops. There are 65,000 ports are available. Keyboard, there is one port. Mouse, one port. Through this port, my computer understands the signals, mouse signals. My computer understands keyboard touches. There is a keyboard signals comes through that port. My computer can access the network, web browsing, website, open website signals, website data always comes through port number 80 or port number 443 or port number 8080, designated port numbers. So there are 2,000 port numbers are designated. Above 2,000, from 2,000, port number 2,000 to port number 65,000, open. So for example, Zoom uses some of the port number, maybe 5,000. All such things. So for cybersecurity professionals, then we can see the ports. So which signals comes through and going out, incoming and going out packets. We investigate all the ports. So this is a computer, and this is, for example, 65K ports. Some ports are open, some ports are closed. Usually, most of the ports are unavailable, right? If you open all ports, then there are lots of programs. Even middle school students, they can scan ports. Some ports are open, then they can get in, right? So almost all ports are closed. How can we close it? We set up firewall, right? You've heard of a firewall, right? Firewall, and then we set up some rules. So only we open these ports for this application, the other ports for another application. Okay, my laptop currently 5 ports are open in the range above 2,000 and below 65,000. Stealthy attack. We see this is when you hide a text M, you convert it to binary code, and you use that binary code here and there. So if that binary code is 0, then you close that port. If that binary code is 1, open it and close. Open it and close. So if some text coming from this particular port, then we can say, oh, this is the second position of that binary code that is set to 1. And then the other, oh, that is the 6th position that's set to 1. If we collect all of those, then that is the messages, okay? Cannot, almost impossible to detect. That type of thing is possible. That's a stealthy intrusion. This is much, much more powerful than information hiding on images. Okay, high enhanced. So lots of those researches available. I know one of our faculty members is working on this. Okay, this is done.
Oh,
yeah.
All right, thanks all. Let's all thank our speaker.
Thank you. Thank you.
So I think we'll start. Thank you so much. I think we'll start if anyone online has any questions, and then Chris, we can maybe then open it up to you after that.
Oh, we have quite a few.
Yeah. So does anyone online have any questions? Let's see.
I know some of you may not catch easily, because I'm talking about from the primitive levels of concept. well, actually, that is what steganography touches. Yeah, all zeros and ones.
So is, in this case, oh, sorry, go ahead, Stephanie, yeah.
Hello. I want to first share that I'm a total novice with regards to this. I thought this was an excellent presentation. I guess my most basic question is there a reason why encryption has replaced stenography?
Oh no, it's not. I'm not saying steganography is a replacement of encryptions. This is the other angle of information hidings. Okay, encryption is widely used, powerful, but on the other hand, there is another area, technology available, which is steganography.
So
This
there
is a
specific
powerful
data that you
if
would
we.
recommend where stenography is not useful.
Oh, this is useful. For example, remember that around the end of Second World War, there's an alliance and United Kingdom. What is the president at that time in UK?
President was Roosevelt.
Roosevelt? No, not. What is his name?
Oh, Truman.
Truman, in America, Truman, but in UK.
In the UK, Churchill.
Church and U.S. alliance try to communicate, but every time it is dropped because the German teams are also very, very intelligent. So they want to inland the French, the west coast, is in Normandy somewhere. They want to make a D-Day. So D-Day, if D-Day, the specific calendar date for D-Day is known, then they can defend, right? So D-Day needs to be securely hidden. They need to, but both the two ends needs to fully understand, right? Between U.S. alliance and Churchill alliance. If we have steganographies, then we send the images. Hey, this is our Christmas celebration photo. Send it to Churchill. Churchill open it and see, oh, this is such a date. Okay. Sharing some secret information secretly between two alliances, then steganography is a good tool. If we encrypt it, then that is, as I earlier said, encryption is a shout out. So everybody knows, oh, that is the message. So let's try to break in. But the images, no one's really see any images because it is silently whispering. So that is one scenario that steganography can fit in more effectively than encryption.
Great, thank you.
You're welcome.
What are the downsides of steganography compared to encryption? Like, is there a reason ever to use encryption instead?
Encryption is always, all the time. That is but steganography is rarely used. Only if we need to share, not allowing anyone else notify.
And I think what Dr. Yoon brought out when he opened up the presentation, encryption, you recognize encryption immediately. You recognize an encrypted letter, which means it triggers your saying, I need to decode this.
Right.
hide in plain sight was the perfect use of the phrase. You're looking at a picture there. Doesn't say anything.
Right.
What
It's not only
is hidden there, the message is in there.
yeah. It's not only the carrier is not only the images. It could be videos. It could be another. I mean, say audio, another
Yeah.
text. So there is our message to send, and there is some other media that we want to use.
And I'm sorry to say, but you know, it's a very useful tool. But bad actors have used this quite a bit.
Right.
Putting in pornography, and particularly in child pornography, they have hidden images that would be illegal inside of other images.
That's a very good
And
point.
that's how
right.
they transported them and trafficked them. So, like everything else, we're talking a lot about AI. There are great uses for it, and it could be a great tool, but it also has the dangerous and bad side.
Mhm.
So that's an example of the bad use of steganography, right? A good use of steganography would be compliance to, and I know in my industry, a lot of times when you're doing work, you have to copy, and what you do is you do screenshots of every stage of something that you're doing. And for compliance purposes, they want evidence of when you did it. It would be good, you could embed, using this tool, the date and other important information into the record, into the image itself, into the screenshot, so that you don't have a file somewhere that says, I did it on this date, and a photograph somewhere. You have a photograph with the relevant text in the photograph that can be pulled out with a script, right, or an API call. So there's two different viewpoints
Mhm.
on the same exact image that we were looking at right there. There's, ports, and we were showing that image. You could have something very vile and illegal in there, or you could have something of great use and value. So, but I think it's important to understand, it's different from encryption, but it's stealth. Whereas
Mhm.
encryption, as he said, it's saying, hey, try to guess the secret that I've got. And that's what the hackers love. I mean, we have people working 24/7 trying to crack your passwords and everything else to get into your bank account and whatever else.
Yeah.
That's the point. This stuff is passing by them unless they are suspicious and suspect that you're using that, in which case then they're going to write scripts to try to detect and find it. But otherwise, it's right under their nose.
We've got a question from Caesar. Caesar, did you have a question?
Yeah, I just had a quick question for Dr. Yu.
Yeah.
I know there was a question that was posted earlier
All right, Susan.
as to why encryption is now a little more popular than what you presented today. Is there a reason that
The encryption. As far as we share the keys, then easy to detect, easy to decrypt, right? Encryption is very easy, and decryption is very easy once we share the key. But steganography is, the detection is state of the art. And also the participants needs to understand equally well. Then one side can hide, the other side can detect. So there is some technical barrier. Yeah, encryption is easier to hide the information compared to steganographies.
Right, and I think my question was then, I know right now it's a little more popular to use encryption than to use
Static.
static right now.
Right.
And just wanted to know what's the reason for that? If we think that the second method, which you mentioned
Yeah.
today, is a little better to use.
Mm-hmm. Yeah. Anyone can do encryption and decryptions. Yeah.
Thank you.
You're welcome.
Are there any other questions from folks online? Chris, do you have another question you want to ask? Or
No, no.
All right, well, I think then in that case, we can thank our speaker again. Thank you so much, John, for giving this talk. It was great. And thank you, everybody online, for coming. And yeah, we'll hope to see you at the next one.
All right. Thank you. Thank you,
you.
everyone.
I got some
Stop
applause for
sharing.
you.